Good morning, everybody. Hope you're all healthy and safe at home. We are moving on to the last section of our fourth module, section 18.4, Cauchy's integral formula, and this is the second lecture regarding this particular section. So in the introduction of this section, I had stated we are going to answer basically two questions which is in our mind. One is how to find the value of a function at a particular point with the help of the contour integral, and that we had discussed in the previous section, which was called the Cauchy's integral formula. Now in this lecture we are going to discuss about another form of Cauchy's integral formula, that is related to the derivatives, higher order derivatives. That is, it is Cauchy's integral formula for derivatives, how we can determine higher order derivative of a particular function at a particular point. So let's see. The Cauchy's integral formula for derivatives is as follows. Let f be analytic in a simple connected domain, and let C be a simple closed contour lying entirely within D. Okay. If z dot is any point within C, then fn of z dot, that is the nth derivative of the function f, is given by the formula n factorial by 2 pi I integral over C f of z by sorry, there's a bracket here, f of z divided by z minus z dot whole raised to n plus 1 into dz. So this is the Cauchy's integral formula for derivatives. So keep in mind the formula, that is fn of z dot is equal to n factorial by 2 pi I into integral over C f of z by z minus z dot raised to n plus 1 into dz. So let's see how we can prove this particular theorem. We are just going to give a partial proof of this theorem. I'm not going to completely prove this. That is, we'll just prove this for the value n equal to 1. That is, we'll find f dash of z dot. Okay, so this is the partial proof of the Cauchy integral formula for derivative. That is the case of n is equal to 1. So the rest can be proved using our mathematical induction method. Okay, if the value is true for n is equal to 1, and supposing that it is true for n is equal to k, then we need to prove the result for n is equal to k plus 1. So you guys can try it out. So here we'll be giving just the proof of n is equal to 1. Okay, so when n is equal to 1, what will be our formula? It will be f dash of z dot will be equal to 1 factorial by 2 pi I integral over C f of z by z minus z dot whole raised to n is 1. So 1 plus 1 is 2. Right. So we have to check whether f dash of z dot is nothing but this value. So 1 factorial is 1 is a. So let's see how we can prove this. First of all, what I'm going to do is I'm going to write what is f dash of z dot. It is by our formula that we have studied. It is nothing but limit delta z tends to 0 f of z dot plus delta z minus f of z dot whole divided by delta z. This is the formula for the derivative. We all know that. Now here what I'm going to do is I'm going to substitute the value of f of z dot and f of z dot plus delta z with the help of Cauchy integral formula. Okay, which we have seen before. So what was Cauchy's integral formula? It stated that f of z dot is nothing but 1 by 2 pi I integral over C f of z by z minus z dot into dz, right? So I can replace f of z dot with this value, and similarly what will be the value of f of z dot plus delta z? That is f at a particular point. So here the point is z dot plus delta z. So this value will be equal to 1 by 2 pi I integral over C f of z is same as it is. Here it will be z minus, instead of z dot we have z dot plus delta z. So z dot plus delta z dz, or I can write this as 1 by 2 pi I integral over c f of z divided by z minus z dot minus delta z into dz. So what I'm going to do is I'm going to substitute this value in this equation. So we have f dash of z dot will be nothing but limit delta z tends to 0. Instead of, I can take delta z and 1 by 2 pi I common, right? So this will be 1 by 2 pi I into delta z into integral over c f of z dot plus delta z dot is f of z by z minus z dot minus delta z dz minus integral over c f of z by z minus z dot into delta z. So again, simplifying this further, that is taking the LCM and simplifying it, what do we get? I get f dash of z dot will be equal to limit delta z tends to 0 1 by 2 pi I into delta z into integral over c. I'm going to take the LCM, f of z into z minus z dot minus f of z into z minus z dot minus delta z whole divided by z minus z dot into z minus z dot minus delta z into dz. Okay, I'm just simplifying it further. So in this case, f of z into z and f of z into z gets cancelled, then minus f of z into z dot and minus into minus is plus, plus f of z into z dot also get cancelled. So the only term remaining will be limit. So after simplifying our bracket, what we get is this is equal to integral over c f of z into delta z divided by z minus z dot into z minus z dot minus delta z into dz. Okay, so I can cancel out this delta z and delta z. So in the end, f dash of z dot, so I want you guys to keep this in mind, okay, the formula that we have derived for f dash of z dot, that is f dash of z dot is nothing but limit delta z tends to 0 1 by 2 pi I integral over c f of z whole divided by z minus z dot into z minus z dot minus delta z into dz. So this is our f dash of z that we have formulated with the help of Cauchy's integral formula that we have learned just now. Now we are going to define a few things, like just keep in mind, first one is f is continuous, right? F is continuous because f is an analytic function, so it is continuous. So this implies f will be bounded. Okay, f will be bounded. So I can write say modulus of f of z is less than or equal to capital M for every z belongs to the given domain. So I hope you guys can get an idea of where I am getting to. Now the second thing that we are going to keep in mind is C is the contour that we are considering, okay, given in our theorem, and let L be the length of the contour. Okay, so can anyone guess where we are going? So yeah, we are moving on to the we are moving on to the ML inequality. We will be using it here. So L is the length of the contour, and the third thing that we are going to keep in mind is delta is the shortest distance delta is the shortest distance between, delta will be the shortest distance between the points on the contour and z dot, the point that we have to find the value at. Okay, so this implies modulus of z minus z dot will be greater than delta, right? Delta is the shortest distance between the points, right? So the modulus of any complex number z on the contour and z dot will be always greater than, it will be either equal to delta or it will be greater than delta, because delta is the smallest one. So from this I can write 1 by mod z minus z dot will be less than equal to 1 by delta, or 1 by mod z minus z dot square will be less than equal to 1 by delta square, right? So this is another thing. And the fourth thing that we are assuming is that suppose that modulus of delta z is less than or equal to small delta into 2, delta by 2. Okay, so these are the things that we are gonna keep in mind right now. That is, f is continuous, so it will be bounded, so modulus of f of z is less than equal to m. L is the length of the contour that we are considering, and delta is the shortest distance, so modulus of z minus z dot is greater than or equal to delta, and in turn we get 1 by modulus z minus z dot square will be less than or equal to 1 by small delta square, and modulus of capital delta z will be less than or equal to delta by 2. So these are the things that we are assuming. Now with the help of this I'm going to find a bound for the integral. That is, now modulus of integral over c f of z by z minus z dot whole square into dz minus integral over c f of z by z minus z dot minus delta z into z minus z dot. This was the last integral that we had found, right? Now this, after simplification, I can write this as again the same thing, right? I'm taking LCM and writing. So here we have to multiply it by z minus z dot minus delta z, and here I have to multiply by z minus z dot. So the same calculation comes. So we'll have modulus of integral over c minus delta z into f of z divided by z minus z dot square, just like we had done before. Taking LCM, we will get this modulus. These two values are equal. Okay, now mod f of z was less than m and length of the contour was L. So by ML inequality, this integral will be less than equal to m into L into modulus of delta z, okay, and divided by, what was this value, less than or equal to, it was less than or equal to 1 by delta square, right? And there was one more value that we had to determine, that was what is 1 divided by mod z minus z dot minus delta z, right? This ML is obtained using the ML inequality, that is integral over c f of z dz will be less than or equal to ML, and modulus of z is mod z itself, and 1 by z minus z dot square was less than or equal to, here it will be 1 by delta square, right? Now let's just see what will be this modulus also. Now how can we do that? Let me just show it to you guys. That is modulus of z minus z dot minus delta z. This I can write, this is greater than equal to modulus of mod z minus z dot minus mod z, right? So this will be greater than or equal to delta, this is greater than or equal to, and this will be greater than or equal to delta minus delta by 2. So this is equal to delta by 2, because we had seen that this is greater than or equal to delta, and this was supposed to be less than or equal to, that is modulus of delta z was supposed to be less than delta by 2. So this implies when I put the negative sign on both the sides, so this will be like greater than minus delta by 2. Okay, so from this we get this is the equation. So here what I'm going to do is I'm going to substitute this in this. So this is also less than delta by 2, right? So I can write this is less than so let me just write it down again. We'll have integral over c f of z by z minus z dot square minus integral over c f of z by z minus z dot minus delta z into z minus z dot dz. Sorry, this d is over here. This will be less than or equal to ml into modulus of delta z by delta square into 2 by our corresponding value, that was into delta by 2. So this I can simplify it as 2 ml mod z by delta q. Okay, by replacing the values of the modulus and which we have just now determined. That is, m was a bound for f of z, l was the length of the contour, mod z remains as it is, and modulus of 1 by modulus of z minus z dot square was less than or equal to 1 by delta square, and modulus of z minus z dot was less than, or z minus z dot minus delta z was less than or equal to delta by 2. So from this we get this inequality. So as delta z tends to 0, what happens? Modulus integral over c f of z by z minus z dot square minus integral over c f of z by z minus z dot minus delta z into z minus z dot dz. This value will tend to 0, right? So that is, I can see that these both are, I mean, I can replace this by limit of delta z tends to 0, this, that is, from this I can obtain limit delta z tends to 0 modulus integral over c f of z whole divided by z minus z dot minus delta z into z minus z dot will be nothing but integral over c f of z dz by z minus z dot square. Okay, so I have obtained that limit delta z tends to 0 integral over c f of z into z divided by z minus z dot minus delta z into z minus z dot is equal to integral over c f of z by del z minus z dot square into dz. We had seen that our f dash of z was nothing but f dash of z dot was nothing but limit delta z tends to 0 integral over c f of z by z minus z dot minus delta z into z minus z dot into dz. This is what we had seen in the very beginning, and now we have seen that this integral is nothing but integral over, sorry, there was a 1 by 2 pi I also, right, if I remember. So this will be nothing but 1 by 2 pi I into limit delta z is nothing but integral over c f of z by z minus z dot whole square into dz. So this is the Cauchy's integral formula for derivatives when, and this is the case when n is equal to 1, right? So The proof was very it is simple. What we had to do is we had to convert the f dash of z dot, the known formula, with the limit condition, that is limit delta z tends to 0 f of z minus z dot plus delta z minus f of z dot by delta z, into a form with the help of the Cauchy's integral formula, which we have learned before. And then we had made some assumptions and found a value we found that limit value. That limit was nothing but integral over c f of z by z minus z dot square into dz. So this is our Cauchy's integral formula for derivatives. Now if you look closely into this formula, if I take this term, that is the n factorial by 2 pi I term, to this side, I can get that integral over c f of z by z minus z dot raised to n plus 1 dz is nothing but 2 pi I by n factorial into fn of z dot. So I can use this formula to determine the contour integral, right? For us, we have to, that is our main problem, that is how to determine the contour integral. So integral over c f of z by z minus z dot raised to n plus 1 will be nothing but n factorial by 2 pi I into fn of z dot. Okay, so we can use this formula to determine that particular integral. So the examples in your textbooks will make this concept a little bit more clear. So let's just move on to these examples. So what are we asked to? We are asked to evaluate the integral z plus 1 divided by z raised to 4 plus 4z cube dz, where c is a circle mod z is equal to 1, right? So keep in mind one thing while we are using this Cauchy's integral formula, that z dot, it will be actually a point which lies inside the contour and the point where the function is not analytic. Okay, because if at that point the function is analytic, then that integral will be 0. That's what we had seen in the previous section, right? So that was our Cauchy's theorem, that if a point is analytic in the particular, if the point there is a point at which the function is analytic, or if the function is analytic inside that particular contour, then the integral will be equal to 0. It reduces to 0. That was our Cauchy's theorem. So here z dot will be actually a point inside the contour where the function fails to be analytic. Okay, so let's see our contour. Our contour is the circle with center 0 and radius 1, right? Now let's see how we can simplify it, or what are the zeros of this denominator. Now I can take z raised to 4 plus 4z cube. I can take z cube common, right? So this is z cube into z plus 4. So z is equal to 0 is a point where the function fails to be analytic, and also z is equal to minus 4 is another point where the function fails to be analytic, right? But z equal to minus 4 is not a point inside our contour, so we don't have to take care about that. So here what we do, we will consider, we have to if you have to find this integral, we need, what all do we need? We need what is n, okay, and we need to know what is f of z, right? Then only we can apply f of z dot. So here z plus 1 by z raised to 4 plus 4z cube can be written as z plus 1 divided by z plus 4 whole divided by z cube. The same thing, we are just rearranging it, right? Here z dot is 0, and what will be n? That is the power, that is z minus z dot, z minus 0 raised to 3, right? So 3 is equal to n plus 1. This implies n is equal to 2. So z dot is 0, n is 2, and what was our function? F of z was z plus 1, z plus 4 divided by z plus 4, right? So this is our f of z. So to apply Cauchy's integral formula for derivatives, the value will be 2 pi I by n factorial into fn of z dot. So here n is 2, so we have to find the second derivative of this particular function. So we'll have to use quotient rule 2 times, and simplifying it, we get f double dash of z is minus 6 by z plus 4 raised to 3. So just verify this, okay, and ask me if you have any doubts regarding this, finding the derivative, second order derivative. So it is minus 6 by z plus 4 whole cube. So we can apply this directly, that is, we know n is 2, and at z is equal to 0, what will be this value? This is minus 6 divided by 4 cube. So that will be 2 pi I divided by 2 factorial into f double dash of 0, which is nothing but minus 3 pi divided by 32 into I. So I hope that concept is clear. Now we'll move on to another example also, which will help you understand this a bit better. That is, we are asked to evaluate z cube plus 3 divided by z into z minus I whole square into dz, where the contour is given in figure 18.4.3. Now the points where the function fails to be analytic is at z equal to 0 and z equal to I, right? So if you see the contour, both the points lie inside our particular C, right? So we have to evaluate at both the values. So what we are doing is we are going to split this contour C into two different contours, C1 and C2, okay? Because Cauchy's integral formula for derivatives is applicable only for simple contours. So this contour is not simple because it is meeting at a point here. There is a intersection point. So simple contours does not have that. So we are considering two contours, C1 and C2. Now note, C1 and C2 have different orientations, okay? Keep in mind. So I'm going to write this as integral over C1. So C1 contains only 0 inside it. Z cube plus 3 divided by z into z minus I whole square dz, plus integral over C2, z cube plus 3 divided by z into z minus I whole square dz. So C2 contains only I inside it. So again we are going to deal with the case when there is a single point inside the contour where the function is not analytic. So C1 has our negative orientation and C2 has positive orientation. So I can write this as minus integral over C1, right? I am changing the orientation. So this is equal to minus integral over C1 into z cube plus 3 divided by z minus I whole square whole divided by z, because 0 is the point where the function fails to be analytic, into dz, plus integral over C2 z cube plus 3 divided by z whole divided by z minus I whole square into dz. Okay, so in both the cases I am going to apply Cauchy's formula, integral formula, to determine what will be the value. So in the first case, if you see, we don't have any powers of z, so we don't have to use the integral formula for derivatives. The Cauchy's integral formula will be sufficient. So by Cauchy's integral formula, this value will be 2 pi I into f of z dot. Here z dot is 0, and what is f of z? F of z is z cube plus 3 divided by z minus I whole square. So that comes out to be 3 divided by minus I square into 2 pi I. So that is equal to minus 6 pi I. So first integral value is minus 6 pi I. Now in the second case there is a power, right? Z minus z dot raised to 2. So 2 is equal to n plus 1 means n is equal to 1, right? So we have, and z dot is I, n is 1, and what will be f of z? F of z is z cube plus 3 divided by z. So we have to find the first derivative, f dash of z. So f dash of z we will determine, and you can apply quotient rule again. So this value will be 2z cube minus 3 divided by z square. So this integral will be equal to 2 pi I divided by 1 factorial into f dash at I, that is 2I cube minus 3 divided by I square. So that value comes out to be 2 pi I into 3 plus 2I, which is equal to 2 pi into minus 2 plus 3I. So the total integral over C, z cube plus 3 divided by z minus I square dz is nothing but minus of I1, that is mine. We had got I1 as minus 6 pi I, and there was already a minus sign here because we had changed the orientation. So this is 6 pi I plus 2 pi into minus 2 plus 3i. So simplifying, we get the value to be 4 pi into minus 1 plus 3i. So this is how we can apply Cauchy's integral formula for derivatives to determine the contour. So basically we use Cauchy's integral formula to determine the contour integral, which are of the form integral over C f of z by z minus z dot into dz. Whereas Cauchy's integral formula for derivatives will be applied, or it will be used to determine integrals in which the denominator, that is z minus z dot, will be having some power. like z minus z dot raised to 2, z minus z dot cube, etc. and so on. So with the help of Cauchy's integral formula, we'll be able to understand, or we'll be able to evaluate the contour integrals in a very simple manner. We just have to find the points where the function is not analytic and check whether they are inside the contour or lying outside it, and make the necessary changes and find the contour integral. So that's it for today's session. Thank you. Stay home and stay safe.